Hello and welcome to Maji Academy once again. Now let us read the question. A transformer has maximum efficiency at full load when iron losses are 800 watts. Copper losses at half load will be option A 200 watt, option B 800 watt, option C 400 watt and option D 1600 watt. The question asks for the copper loss at half load given that maximum efficiency occurs at full load with 800 watts of iron loss. Now, as per the condition for maximum efficiency, a transformer reaches its maximum efficiency when the variable loss, that is copper losses, are exactly equal to iron loss. The iron loss is 800 watt given in the question itself, therefore copper loss is also equal to 800 watt. Since copper loss is directly proportional to square of load, now let us consider X is the fraction of load. Now copper loss at that fraction of load is equal to square of the load fraction multiplied by copper loss at full load. The value of X is half given in the question, therefore copper loss at half load is equal to 1 by 2 whole square multiplied by copper loss at full load, which is 800 watt, which is equal to 800 divided by 4 gives us 200 watt. So the correct choice is option A. Always remember, iron loss is a constant but copper loss follows the square law. If this clear logic helps you, make sure to hit that subscribe button for more exam winning tips. Second question, high leakage transformers are of option A high voltage ampere rating, option B high voltage rating, option C small voltage ampere rating and option D low voltage rating. Usually power transformers in our electrical grid are designed with minimum leakage flux to maintain efficiency and to avoid excessive voltage drop to keep the voltage stable. However, there are some applications such as microwave ovens, arc welding and neon signs which actually require transformers to have high leakage reactance to create a dropping voltage characteristics. But whenever we design transformers with high leakage reactance, their rated current must be low to prevent excessive voltage drop across the reactance. Therefore, they must be of small volt ampere rating. Hence, option C will be the right choice. High leakage transformers are of small voltage ampere rating. Third question, the purpose of the conservator in a transformer is option A to take up the contraction and expansion of oil, option B to prevent short circuit of primary and secondary windings, option C to prevent moisture in the transformer and option D to cool the winding. We know that transformer falls under the category of continuous duty and it is in operation for 24 hours. Therefore, heats get developed. As the transformer heats up, the oil volume increases. This is called expansion. This excess oil flows through a pipe into the conservator tank, raising the oil level there. On the other hand, when the transformer cools, the oil volume decreases. This is called contraction. In this case, the oil stored in the conservator tank flows back into the main tank to keep it full. Thus, we can say the purpose of conservator tank in a transformer is to take up the contraction and expansion of oil. Now, validate other three options as well. Conservator is a medium. Its function is to facilitate the contraction and expansion of oil. Second, to prevent short circuit. In order to prevent short circuit, we provided insulating oil in the tank and also we provide copper conductors with paper insulator. Third, to prevent moisture. This function is carried out by the breather provided with silica gel. And last but not the least, cooling is carried out by insulating oil. By the way, insulating oil acts as a coolant as well as dielectric medium. First question, a 100 by 10 volt 50 volt ampere transformer is converted to 100 by 110 volt auto transformer. The rating of the auto transformer will be option A 100 watt, option B 110 watt, option C 500 watt and option D 550 watt. Here, two winding transformer is converted into auto transformer having primary voltage 100 volt and output voltage of 110 volt. That means it is a step up auto transformer. Now when we convert two winding transformer into an auto transformer, the voltage across the winding and current through it remains unchanged to keep the temperature constant. Now let us calculate the current rating of each winding. Now rated current of high voltage winding is 50 volt ampere divided by 100 volt, that is the rating of winding is equal to 0.5 ampere. Similarly, The current rating of low voltage winding is 50 volt ampere divided by 10 is equal to 5 ampere. Now in this case, current taken from the primary is 5.5 ampere. Since output voltage is 110 volt, that means 100 volt winding and 10 volt winding are connected in additive polarity. However, 10 volt winding is connected directly in series with the load. Therefore, whatever current flows through the 10 volt winding, same current flows through the load. Now, KV rating of the transformer can be expressed as product of voltage and current. Now, taking output side into consideration, output voltage is 110 volt, current through the load is 5 ampere, therefore KV rating is 550 volt ampere. Rather than doing such heavy calculation, KV rating can also be calculated in a shortcut way, that is, KV rating of auto transformer is equal to high voltage divided by high voltage minus low voltage multiplied by KV rating of 2-winding transformer. Here, high voltage divided by high voltage minus low voltage, this factor gives 11, and KV rating of 2-winding transformer is, we know, 50. This product is equal to 550 volt ampere, which is same as the before. Now question didn't mention about the power factor. Let us assume it is equal to unity. Now active power for single phase can be written as VI cos phi. Here product of VI is 550 and power factor is 1. Therefore active power P is equal to 550 watt. Hence option D will be the right choice. In this way, we can calculate the KV rating of auto transformer. In case of power transformer, the no load current in terms of rated current is option A 3 to 5%, option B 2 to 16%, option C 10 to 20%, and option D 15 to 30%. Now we know that a transformer core is made up of highly permeable silicon steel. It is a continuous closed magnetic circuit with no air gap. Therefore, amount of current needed to create rated flux is very less. Now let us come to the topic. When the secondary side of a transformer is open, meaning there is no load, the primary still draws a very small current. We call this the no load current, denoted by I0. It comprises of two components, namely, one is core loss component IW, which is in phase with the supply voltage, and its function is to overcome hysteresis and eddy current loss in the iron core. Another one is magnetizing component. Its function is to set up working magnetic flux in the core, which is in quadrature with the supply voltage. Because of the secondary side is open, no load current drawn from the primary is very small, which is 3 to 5% of the rated full load current. Hence, option A is our right answer. Question: Buchholz relay cannot be used on option A air-cooled transformer, option B 3-phase transformer, option C 500 kV transformer, and option D 1000 kV transformer. Now before validating the options, let us know more about the Buchholz relay. Buchholz relay is a gas actuated relay. It detects internal faults like short circuit and breakdown of insulation. Third, it detects incipient, that is slow developing faults. Last but not the least, very important, this relay is used for oil immerse transformer. Because its operation relies on oil, it is used for oil immerse transformer. Now look at option A. In an air-cooled or dry type transformer, there is no oil. There is also no conservator tank where this relay could be installed. Therefore, a Buchholz relay is physically impossible to use in air-cooled transformer. Therefore, the answer is option A. Buchholz relay cannot be used on air-cooled transformer. Question 7. If a 500 kVA 200 Hz transformer is operated at 50 Hz, its kV rating will be option A 125 kVA, option B 250 kVA, option C 1000 kVA, and option D 2000 kVA. We know that kV rating of transformer is product of voltage and current. Now let us assume current density to be constant. To maintain temperature constant, then kV rating is directly proportional to voltage. Now let us consider EMF equation of transformer, which is equal to 4.44 multiplied by frequency, number of turns, and maximum flux. Since transformer is a constant flux machine, in order to keep flux constant, V by F ratio must be constant. Now from this expression we can write voltage is directly proportional to frequency. Here, voltage is directly proportional to kV rating of the transformer. Therefore, this expression can be rewritten as kV rating of the transformer is directly proportional to frequency. Now let us move on to the calculation part. Here, initial frequency is F1 is 200 Hz. Initial kV rating S1 is 500 kVA. Final frequency is 50 Hz. Now we require to calculate new kV rating. Now let us take the ratio of new kV rating to old kV rating. We have equation like this. Now let us solve it for S2. Now new equation becomes S1 is equal to F2 by F1. Put all those values in the given equation. S1 is equal to 500, F2 is equal to 50, F1 is equal to 200, which is equal to 125 kVA. Hence, option A is the right answer. When we change the frequency from 200 Hz to 50 Hz, kV rating changes from 500 to 125 kVA. Question: the power factor at which transformer operates. Option A 0.8 lead, option B 0.8 lag, option C depends upon the power factor of the load, and option D is unity. We know that transformer is a passive static device. It simply transfers electrical energy from one circuit to another. It does not generate, change, or improve a power factor on its own. The power factor of a transformer is not fixed value. It is entirely determined by the load you connect to the secondary side. Let us understand this concept with the help of example. If load is resistive, nature of impedance is pure resistance, then power factor at which transformer operates is unity. Example of resistive load is electric heaters, incandescent bulbs, etc. Now, if the load is inductive, nature of the impedance is resistance plus inductance, then power factor at which transformer operates is lagging. Example of inductive load is induction motor, fans, washing machine, etc. Now, if load is capacitive, that is combination of resistance and capacitance, the power factor at which transformer operates is leading. Example of leading load is capacitor bank, long transmission line, etc. Hence, from this discussion, we can say that power factor at which transformer operates depends upon the power factor of the load. Hence, option C is the right choice. Please remember, the transformer itself doesn't decide the phase angle between voltage and current. It simply follows the lead of the load. Therefore, the power factor depends upon the nature of the load connected to it. Now let us move on to the next question. Ninth question. If copper loss of a transformer is operated at 7 by 8th full load is 4900 watt, then its full load copper loss would be option A 373 watt, option B 6400 watt, option C 429 watt, and option D 5600 watt. Now let us consider X is the fraction of load, then copper loss at particular fraction of load, which is equal to square of the fraction of load multiplied by copper loss at full load. Now let's move on to the calculation part. Value of X is 7 by 8 given in the question. Copper loss at 7 by 8th of load is 4900 watt. Now put all those values in the given formula. We have equations like this. 4900 is equal to 7 by 8 whole square multiplied by copper loss at full load. On solving for full load copper loss, we will have equation like this. Copper loss at full load is equal to 4900 multiplied by 64 by 49. 49 get cancelled, which is equal to 6400 watt. Hence we can say copper loss at full load will be 6400 watt. In this way we can calculate copper loss at any fraction of load. Now let us move on to the last question. 10th question. Area of hysteresis loop represents option A dielectric loss, option B copper loss, option C hysteresis loss, and option D eddy current loss. Now let us understand the concept of this question with the help of magnetization curve. When a magnetizing force which is applied, the magnetic material is magnetized and the molecular magnets are lined up in a particular direction. However, when the magnetizing force in a magnetic material is reversed, the internal friction of the molecular magnets, that is residual magnetism, opposes the reversal of magnetism, resulting in hysteresis. To overcome this internal friction, that is residual magnetism of the molecular magnets, or to wipe off the residual magnetism, a part of the magnetizing force, that is coercive force, is used. The work done by the magnetizing force against this residual magnetism produces heat. This energy, which is wasted in the form of heat due to hysteresis, is called hysteresis loss. During one cycle of magnetization, one hysteresis loop is created, and the amount of hysteresis loss depends upon the area of hysteresis loop. Or in other words, we can say area of hysteresis loop represents the hysteresis loss. Now let us consider the formula which is used to calculate hysteresis loss, where pH represents hysteresis loss, eta represents coefficient of hysteresis, B maximum is nothing but the maximum flux density, F is frequency, and V for volume. Now let us consider magnetization curve for silicon steel and wrought iron. If we compare the area of hysteresis loop of the three materials, we can say that area of hysteresis loop of silicon steel is least than other two materials. Therefore, hysteresis loss occurring in the silicon steel is least as compared to other two. That is the reason why we use silicon steel for the construction of core of electrical machines. From this discussion, we conclude that area of hysteresis loop represents hysteresis loss. Option C is the right choice.